So let's see this notion of zero element. Okay, so suppose we have a semigroup S star. Okay, so an element I labeled Z in bold, Z, is called a zero element or absorbing element if it satisfies this. Okay, if Z star A equals A star Z equals Z. And this is for any element in S, okay? And as a consequence of the definition, obviously it follows that, Z star Z equals Z. So therefore it's idempotent, correct? So good. So you agree, right? It's an idempotent by definition. Now, here's two abstract challenges that I would like to throw at you immediately. That's why I said this session is short, but I will have interesting challenges for you. And please try to do them before you come to me if you are struggling to answer. And I suggest you join the lectures. I think next week you will have the group stuff also, right, George?
Yes, I will be available same time next week if anybody wants.
Okay, thank you. So the first challenge is that whether this such element Z is unique. So if you have, like, say Z1 and Z2 are zeros in S, it follows that Z1 equals Z2. Okay, try to find out if this is true, if this is if the zero element indeed is unique in a semigroup. The second challenge is a little bit trickier. So we are assuming, just to make it easy, that the two semigroups S1 star 1, S2 star 2, they actually, I'm actually thinking ahead of time. There's another problem, another challenge that I have in mind. Never mind. So assuming that S1 star 1 and S2 star 2 are semigroups, suppose that a map from S1 to S2 is a homomorphism, and the first semigroup S1 has a zero element. The question is if the image of such a zero element is a zero element in the second semigroup. Okay, so that's the second challenge. I told you I'm going to be starting to throw up challenges immediately, abstract challenges, before we go through examples. Okay, so let's see some examples. I think, this is like obvious stuff, right? But there are some tricky stuff. So if the semigroup S star is the multiplicative semigroup of the reals, then obviously the zero element Z coincides with zero, right? We agree? Yes? Okay, yeah, I'm assuming yes. So no disagreement there. Now the tricky question is this one. What if we now take the semigroup S star to be the additive group of the reals? The question is the ordinary zero still a zero element as per our definition? Yes or no? No. Okay. No. Okay. Good. So we all on the same page. Yes, it's true that this is not. It's not zero element. Even though we write it, we call it in the mundane in our mundane life, when we look at this, we just say it's zero. But in mathematics, we need symbols only have a meaning to in relation to the rules of the game that we are playing with. So in this case, we are playing the rules of semigroups, and the definition of zero element, obviously, in the case of the reals with the additive semigroup structure, zero is not a zero element. Okay, and here's another example is obviously the 2x2 matrices over the reals, right? Under matrix multiplication, the zero matrix is obviously a zero, right? And again, if we consider the same 2x2 matrices, and the question is whether this thing is a zero element, the answer is also no, right? So Yeah, so someone is already making some a very interesting, David, very interesting notation. Plus has no zero element. Yes, yes. This is actually, we'll come to this in the next few slides, make a comment on this. Okay, so that's great. And here's another easy example. In this case, obviously, we can see the tables. So, going back to what David is just saying, you can see, even though this notation, in the mundane, as I said, as we're saying, in the mundane, in the normal world, you show this to someone, they will say, oh, it's zero. But for a mathematician, in this case, if you are, playing the rules of semigroups, just through our definition, then there is no zero element, even though, this notation, is what people understand at first sight to be zero, but it is not. What makes zero is how it behaves in relation to the binary operation under consideration, okay? And obviously now we have a zero, right? Because we are considering, in this case, this binary operation that we understand as multiplication, right? Okay, so this goes to the point that David was saying. So, okay. Now another important notion. This notion of now that we have the notion of zero, this enabled us to define another notion. Last week we, in last session, we defined the notion of idempotent. Today we will define the notion of nilpotent. Okay. Am I pronouncing it correct, George? How would you pronounce this?
Sounds good.
Nilpotent. Okay. What about Barry? Do you agree? Barry is not here today. Okay. So, yeah. So everyone, David also agrees. So let's stick up with the nilpotent. Okay. So given a semigroup S star with a zero element, okay, an element A in S is nilpotent if there exists some natural number n such that a to the power of n will yield z, okay? And it follows immediately that obviously zero itself is a nilpotent element, okay? So just by convention, this is just me. Normally, these things would show up in the ring theory type of thing. In the group, also the notion, there is also a notion of nilpotent, but in the ring theories thing, they will call this rad. The notation is a little bit different, but for us, let's just call this nilp of S, okay, to denote the set of all nilpotent elements in the thing in the semigroup S, okay. Now, it is well possible, obviously, that we have in the case this is trivial. So the semigroup only has one nilpotent element. We'll come up to examples in a minute. Okay, and it's even possible that it's empty. So there is no nilpotent element for the semigroup. Okay. And here's a question that I have. You don't have to answer. This is as part of a challenge too, is whether when we have the nilpotent of S non-empty, if it is a sub-semigroup of S. I trust that you will be able to answer this question. This is also pretty easy. And another challenge I have, this is, I labeled this challenge. By the way, in the labeling of the challenge, please, if you see anything wrong, because I think I'm pretty kind of, I'm doubt whether I labeled them correctly. There might be another challenge that I will label 3 or something. But yeah, if that's the case, just remind me that I need to correct the thing. But it doesn't matter anyway. You will be going through the slides. Okay, so this challenge is given S1 star 1 and S2 star 2 semigroups with 0 elements, okay? If we have a homomorphism from S1 to S2, the question is it true that if an element A in S1 is nilpotent, then the image of that element is also nilpotent in the second semigroup, in S2 semigroup? Is it necessarily true? Yeah.
There's a
so this is
the general question in the chat to answer an is it true question. Does it need a proof?
Well, I assume you don't need, if you can see it, if you can compute it on the in your head, then you don't. But I assume you need to try to prove it in order to see whether it's true or not.
I would say either some kind of computational or logical proof or a counterexample.
Yeah, or counter example will do. Yeah, so you don't necessarily, so I'm not necessarily saying, prove that this is just so I'm not giving away. So you actually go and it could be just to add to the confusion, because sometimes when there is a bit of ambiguity, this is where one learns, right?
It's important to try to prove things or try to disprove them.
Disprove them, yeah. Okay, so well, and the good thing is with semigroups, because the structure is so simple, it's just the associativity. That's what we are assuming. A lot of the stuff are really like I won't say piece of cake is like easy. It might be time consuming, some of the stuff, but it's not. And by getting yourself to start to prove stuff when the structure is so simple, this is where you start to build up. You start to solidify, especially as we add more complicated stuff, as the structure becomes more complicated. So I really encourage you. And here are some boring elements. So again, I did the slides very fast. So please correct me later or now if you see any typo. So obviously this is like when the integers with the ordinary multiplication, then the only nilpotent element is 0, right? We agree? We are not assuming whether the semigroup, not necessarily a billion. No. Yeah. Thank you, George. Thank you for clarifying. Okay. So these are all like boring examples, and as we are saying about I think David was commenting on the chat about there is no 0 element when we are dealing with addition. That's why obviously these guys are empty. Okay. So these are like boring examples. Let's see. This is a little bit more trickier. Correct me by doing if this is wrong. I did this that's how you can see why to try to compute it in my head, just came up with these examples. So in the matrix example, obviously the 0 matrix is nilpotent, right? If you multiply it, you get itself. So the non-trivial examples I claim are these, but you can verify this by multiplying them by each of them by themselves. And if the result is 0, then that's it. Then it's 0. And something interesting, maybe these examples are actually terrible examples to comment on this. The trace of nilpotent matrices is 0. Obviously, in this case we have 0, but not because the main not in this case we have the main diagonal. That's why they are like bad example. We have the main diagonal all like 0, so it's obvious that the trace is 0. But not always. You can have also non-trivial examples that don't have where the diagonal is not all zeros, and they are also nilpotent, but the trace has to be 0. Okay, and the determinant also has to be 0, which means that they are non-invertible. Okay, this has a consequence when we go to matrix groups. But we'll come back to matrix stuff in the matrix group section. Okay, so I actually challenge you to try to find other non-trivial examples of matrices that are nilpotent.
Okay, I was about to put a spoiler in, but I won't.
Yeah, okay. Now, we are coming to these very interesting examples again. You will see in a minute. For the time being, we'll start a bit trivial. Yeah, well, in this case, this is empty because as we notice, there isn't even a 0 element when we are dealing with addition. Okay, so this is thrown out of the question. Okay, so let's start. So in the multiplication, Z4, this is non-trivial, right? So help me on the table if I made any mistake. So nilpotent, the nilpotent of Z4 is 0, 2, correct?
Yes.
Yeah, okay, good. Thank you. Now, the question is, are there more non-trivial examples for n greater than 4? Just like last time when the idempotent examples. I'm going to put, first of all, a spoiler alert, is that Z5 is boring too. I claim that the nilpotent set of Z5 is just the trivial element. Obviously, here I'm just considering multiplication. Okay, so if I don't specify when I'm using mod n, I don't specify. I'm using, as you can see, like addition is trivial. It doesn't. We are just considering multiplication. Okay, so the spoiler is that Z5 is trivial.
It's a good
What about Z6?
There was a very good question whether you have to specify left or right multiplication.
That's a very good question. I will leave this. We will come to this when we are getting to monoids anything. Yes. I'll leave this to the next session when we are defining the notion of identity, left and right identity stuff. Okay. So for the time being, let's who thinks, just a gut feeling without checking the table or something in your head, is Z6 trivial? Who thinks it's trivial? Just a gut feeling.
Gut feeling.
Yeah. Trivial? Who thinks it's trivial? We'll find out in a minute because I will share the table.
Okay, there's a longer question in the chat.
Right.
From David. Question 2, trivial to answer if I build the table. Is there a more general way to answer this without examining the table? I can't make a table for Z sub 101.
Yes, there is. Yeah. Yes, there is, but we don't have the toolkit because a lot of these things will require a bit of a ring theory. That's why I'm fudging it a bit. Okay. So someone think, but nevertheless, you will see something very interesting. I would say in a minute. Just bear with me. So let's see the table. Do you all agree? Let's see. Have I made a mistake here? I think it's trivial, right? Looking at the table, or is it not?
Oh, with multiplication.
Yeah, this is multiplication, by the way. Yeah.
Okay.
So it's trivial, right? Yes. So yeah, thank you. The eagle eyes. I wasn't sure. Now, another spoiler alert. Z7 is boring too, the next one. So I'll say that you can verify this at home. In fact, I think I forgot to share did I share the link on Wolfram Alpha that generates this table? So you can go and do it yourself. I'll share the URL. Just bear with me. Actually, I will share it now on the chat. So for the time being, as I look for the URL to share this, for those watching on YouTube, I will share the link on the description. For those who now, I'll share the URL. So before I jump into looking to the to look for the URL, I will just give you a spoiler alert: is that Z9 is non-trivial, and I claim the nilpotent set of Z9 is 036. Okay. And now the question, as I look for the URL to share you, that the URL that generates this table, can you figure out why Z? So far, we have like Z4, Z8, and Z9 are special, are non-trivial. Okay, don't share it. Just hold on the thought. I'll come up in a minute with more tables. So give me just a second to share the URL that generates the tables. You will see more examples, so that way maybe you can see a pattern forming. Okay, let's see. Where is this? Okay, so here's the URL for, I'll paste it now on the chat. There you go. So this is the URL. Oh, okay. This is delete. Is actually I have the wrong document. I'm sharing the slide. Going to be just bear with me. This thing jumping from slide to slide. So this is the thing, the URL that you can use to generate these tables. So let me just close this because it's becoming too many tabs open. I hope the stuff is being done correctly. Obviously, we could doing it manually is a bit it sucks, right? Yeah. So let's find out if this is the case. So here are the tables. By the way, I already done it. I think I printed this, so you can double check. Let's find out first for mod 5. So mod 5. What is mod 5? It's trivial, right? You agree? Mod 5 is trivial. Mod 7. Let's see. Mod 7 is also trivial. Yeah. What about mod 9? Our friend mod 9. What did I say mod 9 was? Let me go back. So mod 9 is non-trivial. So mod 9 is 036. It says here. So let's look at the table. This one. So mod 9, obviously 0 is there. It says 3. Yep. And 6. Do you all agree that mod 9, the nilpotent set is 036? Do you all agree? Looking at this table. Yeah. George, were you asking something? George. And now, these guys, this is a little bit more harder for you guys. I mean, like boring, not harder. Like, thing. I hope I didn't make any mistake also, right? Because the thing, as I said, I'm terrible with concrete examples. So I claim Z10. You can verify on the table that Z10 is Z12 is non-trivial. It has 0.6. I claim. They probably a typo at some point. I don't know. Z13 is trivial. Z14 is trivial. Z15 is trivial. And now we get to Z16, non-trivial. I claim, I hope I didn't make any typo, is that this is it, the 04812. Let's hope that's the case. But nevertheless, even if this is wrong, you will see that Z16 is non-trivial. Z17 is trivial. Z18 is non-trivial. Interestingly enough, Z18 and Z12, like very interesting, or 0.6. Interesting. Okay, I'll leave this as a thing to try to figure it out. I think Sanjay is getting into the more or less into this right direction, but I'll leave this as a challenge on the study group to figure it out why this is the case. For those who are not able to think, then you can ask the rest. And just to give you a hint, these guys, Z20, Z24, Z25, 27, 28, 32, and 36 are also, I claim, non-trivial. So the question is, can you figure it out what's going on? Yeah. George, were you asking something?
No, sorry, I had muted the sound instead of muting my
I saw a
microphone.
question mark, or is it exclamation point?
Oh, I was congratulating someone in the
So
chat.
Dimitri saying, I bet all prime results in trivial. Are you sure? Well, you can double check. Pretty sure. Okay. Well, so Dimitri is sure. Okay. 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 So for those of you, especially the ones watching, if you're not sure about this, just think again, and then maybe you can go back to Dimitri to the thing, and also chat on the study session with George. But as you can see, this is very, very, very interesting. Especially for those of you interested in cryptography stuff. These guys are like the bread and butter stuff. So you need to feel comfortable with the model of arithmetics and their property. Now, here's a question. Now, what if a semigroup does not have a zero element? Can we do anything about it? What's the gut feeling? Can we invent one? Yeah? Yes or no? Am I on, by the way?
I think you can invent anything, but does it do what you want after you've invented it?
So the question is, can we, if the semigroup doesn't have a zero element, can we invent one? Can we invent one? Sure. Okay. Yes, we can. And let's see how we can do it. So the first thing we will do, so this is the thing, we extend the original semigroup, the set, the underlying set, if you will, and we'll label that extension as S0, and it's just the S union with a symbol. I'll call this like zero ball. Well, I won't say zero balls. Like a circle bold. Okay, and then we can construct another binary operation out of the existing binary operation. Let's call it star hat on S0 as follow. Okay, so we say A star hat B equals A star B. So for all essentially for all the elements in the thing in S that originally are from S, we just use the binary operation as it was before. Okay, so that's what we are saying here. Okay, and then when it comes to this special element that we labeled here as this bold element, I won't even call it. I'll call it this. Let's call it this invented zero. We define this x star hat or hat star. How would you pronounce it? Star hat. 0 equals 0 star hat x and equals 0. So this is the thing. So the claim is whether this is this operation defined as defined here makes this set, which includes this special element, into a semigroup structure. Who thinks that's the case? Okay, there's some question. Is this on a fresh slide? So George, can you? I'm not sure what you're asking. Is this on a fresh slide?
I'm still.
Can you hear me? After first of all,
I can hear you. Apparently, I'm muted on my microphone. I'm going insane here.
Maybe I will ask everyone. Is everyone having problems with my slides? .
Testing. Testing.
Am I stuck? Is the slide stuck?
Testing.
Ah, okay. Okay, so maybe, so you still see the nilpotent. Okay. Sorry for that. Let me stop sharing and share again. Okay, so it would have been actually nice if I can get the screenshot of it to see where was it. I guess I have to go back and ask people if so you were able to see this, correct? I see nilpotent up to 18. Okay, so you're not able, I assume you're not able to see this thing here. So maybe actually what I will do is share the URL if you are having problem with the visibility of the slides, because it's view only anyway. So sorry for that. Can you see the slides now? I'm on slide 18. I mean, I've gone back to there on the thing on the nilpotent element just to make sure that we are on the same page before I go to the other slide. Okay, so the next slide is what I was talking. I hope you just correct me if you can see it. Let me go back. So the question, did you see this question? What if a semigroup does not have a zero element? Yeah, okay, here. Yes, sorry. I didn't realize I was just talking and, you guys, you couldn't see what I was talking about. Yeah. So the question was, if S star does not have a zero element, can we do anything about it? And I think I already said it as I was talking through. The answer is yes. And this is how we do the construction, So maybe just for the sake of the thing, I'll repeat again. I hope I'm not, repeating myself. It's just I'll go through it again. So we have the semigroup S star without a zero element, okay? So the idea is we're going to extend it in order to have a zero element. So we do that by, first of all, defining this bold element, let's call it bold 0, okay? And then the extended set S0 becomes the union of S with this singleton element, okay? And then the way we construct a binary operation out of the existing binary operation that we called star hat on S0 is as follow. So we say A star hat B equals A star B for all A, B in original S. In other words, this all we do is to maintain the binary operation between the elements of the S stays as it is. Okay, so but then we say X star so X star hat with this newly added element 0 bold to be defined like this. Okay, to be like the same as 0 bold star hat X, and it's equal to 0 bold. Okay, and this is for all X in the union. Okay, this means obviously that it includes this element itself, right? So therefore, this is as I was asking, I'm asking here. This is nilpotent also, right? Because it's evident from the definition. Okay, so the question is, this forms a semigroup, yes or no? Who thinks it? Yeah. Yeah, so Bob is very fast. Yes, indeed, it forms a semigroup. Okay, so this is how you do you do a extension. You extend it. Next week we'll see we can do the same for the notion of an identity element. If something doesn't have an identity element, well, we invent one. Okay, so this, as you can see, this is like interesting, but feels, yeah, it's interesting. That's why so David is saying interesting because of this challenge. It feels unnatural because you already have the ordinary zero there, and now you are having this other addition there. Yeah, the reason I'm challenging you with this, it's a bit unnatural, is for you to to feel like just to feel comfortable with the with stuff, so not being stuck with the notation, So as I said, symbols are just symbols. The meaning, the way you interpret them, their stuff, their behavior, and these things. In this case of zero, really depends on the rule of the game. In this case, we are obviously, we have the rules that we defined. First of all, we define the rules of this semigroup, right? And we define the property that a zero element needs to have. So based on those rules, whatever we call, zero has to obey that. Whether we have another object that's not like, with similar notation is relevant. Okay. So yeah.
Very good point from
Yes.
Sanjay.
It seems we need to learn. Exactly. So that's why I was saying, in the mundane world, you look at this thing, round thing, you'll say, oh, that's a zero. Well, it depends on the context, which structure are you considering? Okay. So this is abstraction for you. Okay. Don't assume without knowing the ground rules, don't assume things, this is actually, it's going to be like very important for you to not attach yourself with symbols. Obviously, there are conventions that over time people convene, but in this type of stuff, when you're dealing with structures, it's very important to understand that the meaning of the stuff, of the elements of a particular structure really are based on the thing, on the ground rules of the that are underpinning the structure. Okay, you change the structure, you change the meaning and the behavior. Okay, so okay, so enjoy that. Even it's just one. I know it's unnatural. That's actually the right word for it. But nevertheless, I just for you to see how interesting. I mean, especially in the case of additive in editing, in the addition, right? That's the reason. Okay, so now here's another definition, is that of a nilpotent semigroup. So given a semigroup with a zero element, we say that the semigroup is nilpotent if all the elements of S are nilpotent. Okay. In other words, if for any A in S, there exists some natural number n, such that a to the power of n, yields the zero element of the semigroup. Okay. Now, unlike the other places, I was giving you example. Now I challenge you actually to find an example. Okay. I give you a hint here, for example, to start, thinking about matrices, for instance. Okay. So we'll come back to this. All this stuff will continue in the next session. But this is the last bit of this session, and it wasn't much, but I hope you really go through. We are like taking baby steps, but believe me, this will for those of you who are new to this, this will pay off later, because you will be able, your ability to tolerate abstraction will be very, very, very good by going through this this thing, by doing things in this very simplified structure like this. As we add more, you will start feeling more comfortable than if we just throw you a more complex structure like the group structure, for instance. Okay, for those of you who already know, or like are coming from more advanced background, I know this is boring, but bear in mind that the majority, a good chunk of you of the community are actually not coming from a mathematics background. So a lot of this stuff will take them a little bit of time for them to feel comfortable with this stuff. Okay, so that's why we are taking this baby step. But 2 more sessions, I promise you, we will get into groups. Okay, and I'm very confident that even those of you who are new to this stuff, by the time we get to groups, you will start to feel very, very, very comfortable. It won't be difficult, as we go through. Okay, so that's it for today. The slides will be uploaded on this thing on the repository, on GitHub repository. The session will be uploaded on YouTube later. And please join the Discord if you haven't done so, because this is where the study, you can, ping someone else, or if you have any question, you can ask. You can ping people in the community. I know George has been active, the same with Dimitri and the rest. You've been very active. Thank you for that. And Bob as well. George, I believe next Friday, noons Eastern time, you are mostly available, to go through people. By the way, well done. I last Friday I actually checked the chat was very, very active. I saw like the notification 100 and something messages and these things, So thank you for doing this, and all of those of you who are participating. It's really very valuable to the rest, and I really hope even those who cannot join the US time zone, please find someone in your time zone. We have a lot of people across different time zones. Find someone and get yourself into a study session and go through things, because with these things, it's more about practicing and thinking about them. Otherwise the stuff will not sink in. Okay. So George, do you want to say anything? Maybe George is having problem with the microphone. Okay, so George's microphone is not working. That's not a problem. Yeah, but that's fine. I see there is no. So the next session will be. Let me check. So the next session will be April 8th on Friday. I need to start looking at the Eastern stuff and all this. When is Easter actually? So I'm terrible with the holidays. Easter 2020. Let's see. This will be okay on the week of April 17th. Okay, yeah. I think that week we won't have lectures anyway, so we are good. Yeah. So the next session will be on April the 8th. You will next week receive a link to the registration page once it's once the thing is up. I see, or at least operators. It is important to see which parts of the semigroup definition are needed for these questions. Yeah. Some of the symmetrical must be nilpotent. Yeah, good. I'm enjoying this chat, and I really encourage you guys to take it over to Discord, and especially next week in the study sessions. We go through the stuff. I'll just go back again. I know we've been like taking baby steps. Believe me, this thing will get harder. And if you haven't gone through this, it will be a little bit more harder as we get to the actual group theory section. Yeah. So. Next, so the plan is next session we will definitely transition into monoids, and we will, define. Now we have a zero element. Now we need to define, the notion of, identity in the multiplicative sense. So we will recover the unit stuff in next week, and just like we did today, if a semigroup doesn't have an identity, we can always extend it and have it. You will see how the same procedure will happen. Okay. Yeah. So so George is saying the grown-up steps will be harder without mastering the baby steps. Yes. Thank you. That's, I couldn't agree more. Very often, one is anxious to jump straight into the hard stuff, but doing it this way is like in sports, right? When you start practicing for whatever sports, especially in the early season, you don't immediately start like going to doing the hard stuff. It's like a progressive stuff. So this is more or less the philosophy that we are taking in order to give people the opportunity to to get the stuff in small doses, so they can make progress as we go harder. Yes, semigroups have useful applications. It's pity that we don't have functional analysis and this type of stuff yet, but they will come back later when we're talking on anything in the operators. This stuff is very, very, very useful. Anything. So, and other things too. In the automata theory, all this, systems. Yeah. The reason I'm not emphasizing a lot on them is because obviously we are mostly focused on groups. That's why, we are just skimming through these guys, but all of them have very useful applications, in the monoids, for example, in functional programming, for instance, all this stuff, they are very, 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 very useful stuff, and the main motivation really to go through, instead of diving straight into groups, by doing it this way, some of the notions that carry over, you will see how they change, and some of the notions, you will see that some of the properties will not carry over to groups, and this is also part of the stuff of learning process that I think will be very useful to you. Okay, and the next talk is speaking about events. So we had Owen give a talk on symmetry, on group theory. So the next session that we will have, like a guest speakers, will probably be after we start group theory, because I want the first session to be on the Diffie-Hellman key exchange protocol on cryptography. So, by the way, thank you, George, for spotting the typo. I think I must have been using a word stuff that auto-corrected me to Diffie-Hellman instead of Diffie-Hellman. So thank you for the correction. I will correct the slides and then update them at some point. Yeah. So anyway, the next talk will be on. I want it to be on cryptography, because then we will have, especially when we cover generators and this type of stuff, that we need all the key concepts that we need in order to understand the Diffie-Hellman key exchange protocol, and then we will have someone give a guest speaker to give a talk on the applications of the Diffie-Hellman protocol. That way you can actually see it, just the stuff that you learned the week before or something, how it's being used to keep our communication secure, for instance. So I really look forward to it. And then once we get to these guys, like these guys, the orthogonal group and special orthogonal group, will have someone to do a talk on machine learning. Even though this will be, we also have this when we get to Lie group stuff, but nevertheless there will be some of the stuff that are going to be useful, in particular in geometric deep learning. And then hopefully once we get to this, we'll also have someone in this unitary group and special unitary group. We'll have someone give a talk on quantum computation. In particular, I'm interested in quantum error correction, for instance. So plenty of motivation, side stuff just to keep you motivated, and we will still have them as we get to actual Lie group stuff. So, but we'll have enough for you to be able to have some basic understanding of how these things are applied. Okay, so I don't have anything else to share. If nobody has any question or any comment, I'm happy to end here, and we can catch up next time. Okay, good. So it seems like nobody has any question. Thank you, George. I know your microphone. There is a problem with your microphone, so that's fine. It's okay. No, don't worry with that. And I look forward to seeing you all next time. So yeah, be patient. We'll get to groups. So yeah. So I'll see you next time. Thank you so much, and have a good weekend. Okay, let me stop sharing. And bye for now. I'll see you next.